So I started to talk about the possibility of defining Ricci curvature lower bounds on metric measure spaces last class. And I sort of said, well, we can hope to do this in terms of hypothesizing the convexity of an entropy function, such as the rho log rho Boltzmann-Shannon type entropy. So it turns out that so basically when, 20 years ago, the open problem was to find a notion of lower Ricci curvature bounds, which coincided with what it would be in the smooth differential geometric case, and which was stable under taking limits in an appropriate sense. And so somehow the spirit of this is like passing from the rationals to the reals. So you can definitely have a sequence of smooth Riemannian manifolds with even lower sectional curvature bounds, and maybe upper bounds on dimension diameter or something, whose limit is something like a convex polytope in a limit in appropriate sense. And the convex polytope isn't smooth anymore, but it still has nice properties where somehow the convexity follows from, say, having a sectional curvature lower bound of 0. And it still has things like geodesics, at least, and the geodesics are pretty nice, at least almost everywhere in some sense. So the philosophy is sort of, we'd like to where the smooth Riemannian manifolds are a bit like the rational numbers, because they're not a complete set, and there are various natural notions of limit in which you would obtain singular objects, and you'd like to be able to complete them. And so in some sense, this theory of metric measure geometry provides a framework for dealing with the completion of the smooth Riemannian manifolds under lower Ricci curvature bounds. And so you want limits to inherit these lower Ricci curvature bounds. And the third property you want, if you had a metric measure space with a lower Ricci curvature bound, is you would like it to have some non-trivial consequences. So for example, you'd like to be able to derive things like the Brunkowski inequality or isoparametric information. And so I'm actually going to tackle the third problem first, the problem of non-trivial consequences. And the thing that I'm probably not going to tackle in this course is the equivalence of the convexity of Boltzmann's entropy to a lower Ricci curvature bound of 0 in the smooth setting. Because to show that equivalence, first of all, it requires you to have some familiarity with smooth Riemannian geometry, which maybe not everyone does. And secondly, it takes a while to build up machinery to do it. And I've done it in a course before, but it takes too many weeks for me to want to do it this time around. So what I'll try to do today is talk about consequences, and then hopefully still in the future, I will talk about the preservation of these lower Ricci bounds under limits. But first of all, in order to have non-trivial consequences, it's not enough to have just, so there are various refinements of the notion of convexity, which it's useful to have. And so, so here's a definition. If K is a real parameter and N is maybe between 1 and infinity, sometimes people deal with negative N's as well. We say a function S on the reals, maybe taking plus infinity as a value, is Kn convex. If and only if two things hold. Well, S is semi-convex. And secondly, semi-convexity of S means that the second derivative of S is non-negative. And if I want to, sometimes I want to strengthen or weaken this property of, semi-convexity means you have a lower bound for the second derivative of S. And sometimes you want to strengthen or weaken this property. And so depending on the parameters K and N, I can ask for S double prime to be bigger than S prime of R squared with a power 1 over N in front of it, and maybe plus a constant. let's say almost everywhere. And so semi-convexity basically means there's an interval where S is finite. And inside that interval, the second distributional derivative of S has a lower bound. Okay, and here the lower bound. If n is infinity, then we don't have this first factor, and then the lower bound is just the real parameter k. And if n is less than infinity, then we're asking for a slightly larger lower bound, depending on the slope of S. And so some remarks are, the larger k is and smaller n is, the stronger this property. Right, the right-hand side is monotone non-decreasing in k and monotone non-increasing in n. And a second remark is that the integers k and n are sort of fake in some sense that if we looked at scaling, so remark 1, remark 2. So if I scale the R variable, the argument, the first two terms go the same way. So if I replace R by alpha R, I'm going to get a 1 over alpha squared in front of the first term and a 1 over alpha squared in front of the second term, and I'm going to get nothing in front of the third term. And so scaling that means that without loss of generality, I can take k to be either plus or minus 1 or 0. And then the second observation is that if I scale S by beta S, I'm going to get a beta in front of the first term and a beta squared in front of the second term. And so I can basically, I can scale n to be 1 if n is finite. And I probably ought to do the scaling in the opposite order. I should probably first scale S to make n equal 1 and then scale R to make k equal plus or minus 1 or 0. So of course, this scaling only works if n is finite. If n is infinite, then you can't scale it away. And the second observation is that just like convexity, so recall S prime prime bigger than 0 on R is equivalent to S of 1 minus Tx plus Ty being less than 1 minus Ts of x plus Ts of y for all x, y, and R and t between 0 and 1. We want some kind of analog of this equivalence that holds not just when k is 0 and n is infinity, but for arbitrary k and n. This is the case. Kn equals 0 infinity. And we'd like an analog analog for other k and n. And so I got a theorem somewhere. I wasn't clever enough to print out my notes. But let me have a look. Right. Here we go. I'll give a try to printing it now, but it's even gonna, I think it's gonna work. Okay, so let me see. So what was the what's the analog that I'm looking for? So here's a version that's so here's the theorem, and you can compare this with in Cedric Villani's big book, Theorem 14.28. Oh, right. So the following are equivalent. Let's see. Under the hypothesis that well, so okay. So let me say just the following are equivalent. So Villani makes this hypothesis that S should be continuous on 0, 1, and twice continuously differentiable on the closure of, sorry, the other way around. It should be continuous on the closure of 0, 1, and twice continuously differentiable on the open interval. Implies the following are equivalent. Property 1, Kappa 1, convexity, i.e. S double prime minus S prime squared bigger than Kappa, either 1, 0, or minus 1. Second equivalence, if I define U of R to be the exponential of minus S, then it satisfies a linear. So this is, of course, a nonlinear inequality. But if you exponentiate S, then it satisfies a linear inequality, namely U double prime less than minus kappa U. And the third equivalent property is that it's actually going to be, instead of a convexity inequality, it's going to be a concavity inequality for capital U, because basically because this minus S in the exponential turns a convex function concave. And the concavity inequality is going to be that capital U of 1 minus T x plus Ty is bigger than something, some coefficient, depending on T. And so let me call the coefficient sigma kappa 1 minus T of, it's going to depend on the magnitude of Y minus X. Sigma kappa T Y minus X of Uy. So these sigmas here that depend on kappa, which if kappa is 0, then it's just probably 1 minus T and T. But if kappa is non-zero, it's something slightly different, where so this is again for all X and Y in R and t between 0 and 1. But I need to say what the sigma kappas are that take the role of 1 minus t and t in the usual convexity or concavity inequality. So where sigma t kappa of R is going to be, let's say, S kappa of TR over S kappa of R. And here R needs to not be too big. When K is positive, R needs to not be too big. So when kappa is 1, R squared needs to be less than pi squared. And right. Let me maybe take this out. Okay. And I haven't told you what SK is yet. So SK of R is if kappa is positive, then it's sine of R square root kappa. So in other words, kappa is 1. It's hyperbolic sine of R square root kappa if kappa is less than 1, if kappa is less than 0. Sorry. And it's just R if kappa equals 0. So you see that this sigma t is independent of R if kappa equals 0, and it just equals t. And otherwise, it's approximately, by Taylor expanding sign or hyperbolic sign, you see that sigma t is approximately equal to t when R goes to 0, but it's something which continues nonlinear in a different way. So is the statement clear? And so I'm going to spend a little bit of time proving this theorem, the equivalence. But okay. Sorry, this is not so legible, but there we go. So this is exactly an analog for this statement here, and the inequality goes the other way because of the minus sign. And you can imagine, because the second U satisfies a linear differential inequality, whereas S satisfies a nonlinear differential inequality, you can imagine it's more convenient it's often more convenient to deal with U than S. And of course, I've stated this equivalence for kappa 1 convexity, but because of the scaling arguments that we made a little bit earlier on, there are analogous equivalences for Kn convexity for other Ks and N. They're just more complicated to write. So in fact, maybe I should, I'll try to put it in color, how this would look for other Ns. So I think there would be a 1 over N here, and you'd have a U sub N, and it would be defined as minus S over N. And then this would be the same inequality, but kappa would be equal to the ratio of K to N. And that's more or less the story. So you probably can't tell the difference between my kappas and my Ks, and I apologize for that. I'll try to make the K even bigger. Okay. Okay, so let me try to sketch the proof, or say some parts of the proof. So actually, does anyone recognize the equivalence between 1 and 2? So those of you that have taken a graduate partial differential equations course may recall that the Hopf-Kohl transform turns a nonlinear equation that looks a bit like this guy into a linear equation. It takes a nonlinear Hamilton-Jacobi equation, a viscosity regularized Hamilton-Jacobi equation, it's an exponential transform that turns it into a heat equation. And that's basically the same thing that's going on here. So the equivalence between 1 and 2 is a special case of Hopf-Kohl transform from PDE. So in other words, if I set if U is some nonlinear function of S, then of course it's easy to compute the derivatives. U prime will be phi prime times S prime, and U double prime will be phi double prime S prime squared. There's the nonlinearity, plus phi prime S double prime. And then you see that if I look at S double prime minus S prime squared, and I want that to be equal to some function K of R, that's going to be true if and only if U double prime, which is phi double prime plus phi prime S prime squared plus phi prime KR so this is what I've written. I wonder if, let's see. Right. So if I have a formula here for U double prime, and if I use this guy to substitute in for the S double prime, then I get this. And if I want to simplify this, I'm sort of lost as to why I have this on the right-hand side, actually. But if I want to simplify this expression here, then it's very useful that phi double prime plus phi prime should be probably 0. So if I take, in other words, if I take phi of S to be e to the minus S, then phi double prime and phi prime are going to have opposite signs, and this is going to be equal to 0. So then I'll have this is supposed to be motivating the choice of U to be this exponential, and then I'll have, with that choice of U, I'll have U double prime is phi prime of KR. Great. And then with this choice, phi prime is the negative of, so this is the negative of U, which is exactly where I got this. Great. And so, in other words, the right-hand side here and the right-hand side here, because this choice makes U non-negative, this right-hand side and this right-hand side have opposite signs. And that's basically the equivalence of 1 and 2. Right. This would be equal to some expression if and only if this is equal to expression and this guy has the opposite sign to that guy. So opposite signs. And I guess the assumption on S that it was twice continuously differentiable on the interior justifies all the derivatives that I'm taking. And if I didn't have that, I would have to worry about in what non-smooth sense these various things hold. Okay. So we also want to see the equivalence of either 1 or 2 to 3 with these funny choices of coefficients. And by the way, another way to motivate this these choices of the SK are to say that regardless of the sign of K, if I take 2 derivatives of SK, I get something like S double prime plus S equals 0. So it's the solution to maybe plus kappa S. It's this, what's written here is the solution to this ODE subject to the initial conditions that S kappa of 0 equals 0 and S prime kappa of 0 equals 1. Okay, so I wanna show the equivalence of 1 or 2 to 3. And one direction is basically Taylor expansion, and the other direction is the maximum principle. So the sort of easy direction is that 3 implies 2. This is the easier direction. And this is basically Taylor expansion. So, so we can assume, wait. Oh yeah, right. So let me actually, so for this part, let me actually state this in the form that Fulani stated it. So sorry. So I'm going to state Fulani's theorem, which is in a slightly different. Fulani 1428 says this is now a theorem for kappa in R. And it basically says the following are equivalent under the same hypotheses. U double prime plus kappa U prime is negative in 0, 1. And if kappa is less than pi squared, then for all r's between 0 and 1, we have the same inequality u of 1 minus t r naught plus tr1 is bigger than sigma 1 minus t r naught minus r1. I guess I should have put absolute values here. Oh, I guess it doesn't matter whether I have the absolute, so SK is odd, but the ratio of SKTR to SK of R is even, so the absolute value signs don't matter. The absolute value signs are redundant. So this is Fulani's statement. And as I said, that 3 implies 2 is the easier implication. So I've abstracted this from Fulani. By the way, his proof is full of mistakes. There are but minor mistakes that can be corrected, but lots of typos, lots of inequalities going the wrong way, lots of wrong powers on expressions. So the easier direction is that 3 implies 2, but still there was one direction that I had trouble with, and I got enough clues out of Fulani to correct, to put a proof together. So first of all, you can assume kappa in this normalization where r is between 0 and 1, you can assume kappa is less than pi squared, because otherwise 3 never happens. So in other words, well, what's special about pi squared is that, so we wanted, so, oh yes, u is positive. So maybe I should write that somewhere. For u bigger than 0, the following are equivalent. Basically, when you solve a differential equation like this with kappa positive, you get a sine or a cosine. And the sine of the cosine, the period of the sine of the cosine is proportional to, is maybe like the reciprocal of 1 square root of kappa or whatever. But the point is that if you sine the endpoints, let's say kappa is 1. So then you want a positive function that solves u double prime plus, sorry, this shouldn't be a prime here. That's a typo. So I have some typos of my own. Good. You want a positive function that is the negative of its own second derivative. And if you try to define a positive function like that on an interval bigger than 0 pi, you're out of luck, because sine and cosine both oscillate with frequency pi. And so no matter what linear combination of them you take, you're always going to become 0 or negative somewhere if the interval is too big. And so that's why I need to assume in this normalization kappa is less than pi squared, since otherwise 3 doesn't happen. But then otherwise, these coefficients here that we said would be plus infinity else are plus, so there was this condition. If they're plus infinity, and then you're asking for, you have plus infinity on the right-hand side here, so you're asking for plus infinity on the left-hand side. Since otherwise 3 doesn't happen. And so the implication holds trivially. And then Taylor expansion says that let me fix t to be 1/2. And then I want to look at some, let's say, r. And so this is something like a ratio of hyperbolic sine or sine of 1/2 r to the same function of r. And so to first order, that's 1/2. Right, so this is something, so maybe I write it out. This is something like 1/2 r minus 1/3 factorial 1/2 r cubed. And then plus something of order 5. And this is something like r minus 1/6 r cubed plus something of order r to the 5th. And so this ratio is something like 1/2 times 1 plus kappa over 8 r squared plus something of order r4. So I guess there's a kappa here. And also, because we assumed u was twice continuously differentiable if I expand 1/2 u at r naught and by the way, I'm going to use this formula, the above formula. I'm going to expand 1/2 u of r naught, u of r1. And if I set delta r to be r1 minus r naught, then if I expand around the midpoint, the first order terms are going to cancel each other since r1's a little bigger, r0 is a little smaller than the midpoint. And the second order terms are going to involve u double prime at the midpoint. And then it'll be delta r squared. And it's over 2, but I mean, I guess, right, the distance from the midpoint is like delta r over 2. So when I square that, I'd have delta r squared over 4. And then I'm basically adding these two things together, but I'm also dividing by 2. And so in the end, and there's a 2 factorial in the end, I get an 8 here. And it's the error term is little o of delta r squared, smaller than delta r squared as delta r goes to 0. And so I want to combine these two Taylor expansions, but I'm going to, the r upstairs is going to be delta r when I combine them. So this will be delta r here, and it'll be 1/2 1 delta r squared plus order delta r fourth. So I'm going to basically, so as delta r goes to 0 with fixed mean, I'm going to multiply these two things together. And what's the hypothesis? I'm wanting to show that 3 implies 2. So my hypothesis is going to be that oh yeah, the nice thing is that when you take t to be 1/2, then the coefficient here is the same as the coefficient there, and you can combine them. And that's why I want to multiply this coefficient times this sum here. And I'll have u at the mean on the other side. And so bringing this u at the mean over to the other side of the inequality before I multiply gives me 0 is bigger than sigma 1/2 delta r ur naught plus ur1 minus ur, r being the mean here. And so, of course, because of this leading order term of 1 here, or 1/2 rather, the leading order term vanishes, and the only things that stick around are these coefficients of r squared. And so you get that this is 0. And then you have this delta r squared over 8. And then you get a u double prime term from here. And you get a kappa u term because I've multiplied this by u. And then you get lower order corrections. And so now finally taking the limit as delta r goes to 0, I get that this has to be negative, and that was what we wanted. That's 2. So this is 3 if you like, and I just derive 2 from it. Other questions? Okay. And so the more sort of PDE kind of direction, the harder direction is that 2 implies 3. And I'm going to rescale to do this. So I'm going to write ut is capital U of 1 minus t r0 plus t of r1. And with this rescaling, what 2 says is that u double prime plus, this is effectively, I've effectively rescaled kappa by the distance between r0 and r1. So u double prime plus kappa delta r squared now, little u is less than 0. And we'd like to derive this kind of differential, this kind of inequality from that. And so case 1 is that if we're in the kappa negative case, I'm going to let, so there's a little bit of gymnastics you need to do. So of course, we're always dealing with positive functions. So I don't think I need to fuss much. So u is positive here. I'm going to let v of tau solve v prime prime plus kappa v equals 0. Instead of inequality, I'm going to assume equality here. And I get to choose 2 boundary conditions. And so basically, I'm going to assume that v of 0 equals u of 0 and v of 1 equals u of 1. So the picture is that, I'm now on the interval 0, 1, and I have some function u, which satisfies this differential inequality, which is a little bit in the vein of saying that u is, if kappa was 0, it would be saying u is concave. So whatever its values are here and there, it has the flavor of being concave in between them. That's like u. And then I take this v, which if kappa was 0 would be the straight line connecting these things. And if kappa is negative, it's not a straight line anymore, but it's something else. But it agrees with you at the 2 endpoints. And then the theorem, or the conclusion that so what's the point? The point is that what appears on the right-hand side of this exactly saturates the differential inequality. It makes the differential inequality into an equality. And so what appears on the right-hand side of this after I do the rescaling, so this is now little u, what appears on the right-hand side is actually just v. And so what I'm trying to show is that u stays above v. That this differential inequality implies u stays above v. So basically these, remember we chose these coefficients, the sigmas, and these should be sigma kappas, I guess. We chose the sigma kappa to exactly saturate a second order linear equality subject to the appropriate boundary conditions. So of course the boundary conditions here are both at one endpoint, and I'm prescribing the value and the derivative. And over here, I'm prescribing the 2 endpoints instead. But if you think about what these terms are doing, they're exactly cooked up so that you satisfy the 2 zeroth order derivatives at the 2 endpoints. Right? When t equals 0 here, sigma is 1. And so this is equal to ur 0. And sigma t is 0, and vice versa. When t equals 1, this term is 0, and I exactly get the value u at the other endpoint. And the sigma if I think of sigma being a function of t, the denominator here is fixed. And so the numerator is exactly satisfying the second order equality, differential equality. Okay, so my claim that I'm trying to show is that u stays above v on the entire interval in that case. And so if not, then there would exist a t star somewhere between 0 and 1, where we choose t star to be the minimum for the difference, minimizing ut minus vt. So so what would happen? So u double prime of t star minus u v double prime of t star would be positive. And now the differential inequality tells me that u double prime is less than kappa u. And the differential equality tells me that v double prime is equal to kappa v. And if this is always positive, then this difference here would be negative at that point. Minus, since kappa is negative, minus kappa is positive, this difference would be negative, and I have a contradiction. I have 0 strictly less than 0. So a contradiction unless u of t star is bigger than or equal to v of t star. And so that shows that that u is bigger than v everywhere. And that's basically what we wanted to show in step 3. U at the midpoints is bigger than this particular combination of u at the endpoints. Questions?
Do I have delta r squared in a differential equation?
Sorry, do I have delta r squared? What?
In the equation of v, I mean.
Yes, I rescaled it. So you're telling me that this should be multiplied by delta r squared. Is that right? Or
and also the ODE for v.
Yeah. Right. Thank you. Yep, exactly. But delta r squared is a positive quantity, so we're safe. Other questions? So that's the case kappa negative. The case kappa 0 is even easier. Let's say kappa equals 0 is standard because this is basically standard concavity. So then when kappa is 0, this inequality is just saying u is concave. Sigma 1 minus t is, this is 1 minus t, and this is t, and this is just an alternate equivalent expression for concavity of capital U. So the case kappa equals 0 is standard, and the case kappa positive is slightly trickier, but of a similar flavor to what we just did. And this one, I think Fulani botched up the proof. But so first of all, first thing Fulani does is he worries a bit about making sure that if u is just non-negative, you can perturb it to make it positive by adding an appropriate sine or cosine. But I'm not going to worry about that because I'm only interested in applying this to positive u's anyways. So without loss, assume u is positive. Maybe even on the closure. And so we want to basically just define v as above. So again, v of 0 is going to agree with u of 0, and v of 1 is going to agree with u of 1. And oh yes, I'm going to assume kappa is less than pi squared because Otherwise, I wouldn't be able to get V positive on the whole interval. And maybe I should put an epsilon here. And let's see if I can. So basically, well, so V0, V epsilon would solve the differential inequality. V double prime plus kappa V epsilon equals 0. And then I need to perturb, I probably want to perturb this slightly. And I'm not sure whether it's a plus or minus epsilon that I want to add here. So I'm not, so we'll figure that out as we go through the proof, hopefully. And I hope that the epsilon's multiplying the V and not outside it. But we can think about V0. It's clear what V0 is supposed to do. V0 is the one that we dealt with before. And then we'll worry about perturbing it later. So it's enough to show, if we show U is bigger than V epsilon for all epsilon positive, then the limit, then U will be bigger than V0 also, which is what we want to prove as desired. And we're going to assume, and we're going to look at oh yes, and because this interval is not too large, we can, and epsilon is sufficiently small, the solution to this differential inequality doesn't require more than half an oscillation of a sinusoid, and so V will be positive as well. So V is going to be positive if epsilon is sufficiently small. Okay, and then we're going to apply the maximum principle, this time not to the difference, but to the ratio. So we're going to consider U over V epsilon, I think. So that's why I needed V to be positive, because I don't want to be dividing by 0. And it's still, this is going to be as smooth as U was and continuous up to the endpoints. And if U over V epsilon is minimized at t being 0 or 1, we're done, because then U is bigger than V epsilon in the interior. And otherwise, it's going to be minimized somewhere in the interior. Of course, so maybe I should call this T epsilon, because now it's going to depend on epsilon. Otherwise, there's an interior minimizer where we're going to know the second derivative of this is non-negative and the first derivative vanishes. So 0 is going to be less than the second derivative of U over V epsilon. And that's, according to the quotient rule, that's U prime V epsilon minus U V epsilon prime over V epsilon squared. And if I apply the quotient rule again, the cross terms are going to vanish. And so I get something like U double prime V epsilon minus U V epsilon double prime times V squared minus 2VV prime U prime V epsilon. This is always V epsilon minus U V epsilon prime over V to the fourth, V epsilon to the fourth. And then if I rewrite that using the differential inequalities, then this is, oh no, wait, I just want to, sorry, I don't want to use the differential inequalities yet. I just want to add and subtract the same thing. So this is like U double prime plus kappa delta R squared u over v. And then I'm going to suppress the epsilon. It's u over v squared, and then v double prime. And I added in a term here. I'm going to subtract it back out here. And I notice that this here is like what's inside the first derivative. So this is like since the first derivative vanishes, what's left over is basically minus 2 v prime over v. Oh yeah, here's the first derivative vanishing. This term is going to go to 0 because this is the first derivative. Great. And so this term here is less than 0.
Oh, sorry, Robert. What's the last term on the right?
Yeah, so this is minus 2 v prime over v, u over v prime. And u over v prime is 0 I'm evaluating at t epsilon, where u over v is 0, and so this first term is less than 0. And this term, if I had the k plus or minus epsilon here, it would be equal to 0. And so what's left over is something like minus u over v squared, epsilon, this is v epsilon squared, epsilon delta r squared v. And it's plus or minus here, minus or plus. And so now I guess it's clear that I want to choose the plus before, so I get minus here, and then that's a contradiction. I have 0 is less than something strictly negative. So I think, according to what I just did, I want to choose the plus here. This term is, sorry. This term here is 0 at t epsilon. And so I get the same kind of maximum principal contradiction. Okay. And, Fulani, so we made this assumption, and then Fulani has cases D and E as well, which are like D and E have to do with the case kappa equals pi squared, or maybe kappa is bigger than pi squared. I don't remember. Showing that the theorem is still true in those cases as well, but I'm not gonna fuss about that. Any questions? Great. So we now have this. This is going to be our workhorse. This new expression for McCann convexity. That we define it in terms of this differential inequality on S, but we're actually going to use it in terms of this pointwise inequality on the exponential of negative S. Oh, and it's nice to let me put in a remark as well. Of course, so point 2 was that u double prime plus ku is negative. It's saturated by u of r is for example, cosine of r square root kappa. Maybe I shouldn't. So that's when kappa is bigger than 0. It's hyperbolic cosh. Also, you could also use sine. It's also satisfied by sine or combinations. If kappa is less than 0, you need to put a minus sign in front of kappa. And I guess it's saturated by R if kappa equals 0. And so the corresponding S is correspondingly if I have k bigger than 0, S of x would be minus n log cosine of x square root k over n. Is k unconvex? On whatever the maximal interval is, I guess x between, when kappa is 1, it would be the interval between pi over 2 and minus pi over 2, and otherwise you'd scale it by n over k. And similarly, when kappa is less than 0, the kn convex function that exactly produces equality in the kn convex condition would be minus n log. This log is basically undoing the transformation from s to u, hyperbolic cosine. And that one works on the whole real line. And when kappa equals 0, it's just straight log, and it's defined on the half line. So these functions are sort of the prototypical examples of kn convex functions to keep in mind. And so you see, even when k is 0, it's not quite, if n was infinity, s would be linear or affine linear, but since when n is finite, it's somehow logarithmic instead. It's minus a logarithm, which is a little bit more convex than something linear. So this, when n is finite, it strengthens the notion of convexity. When k is positive, it strengthens the notion of convexity. When k is negative, it weakens the notion of convexity. All right. So now my our definition is going to be so now fix a Polish space MD with reference measure M. And sorry, this is supposed to say Borel. Right. So in some parts of the literature, they always, when they write MD, they mean M to be a manifold, and they write XD when it's just a metric space. I'm going to use capital M and capital X interchangeably, I think. And the reference measure will be little m. And we say, and we're going to define the Wasserstein distance D2 on the Borel probability measures on M. And we're going to define Boltzmann's entropy, S mu, to be integral d mu dm log d mu dm integrated against M. If mu is absolutely continuous with respect to M and plus infinity else. And we'll say MDM satisfies the curvature dimension condition with parameters k and n if and only if well, so there's a little bit of an issue. So I'd like to say, yes, okay, let me say it. For every mu naught and mu one in the probability measures with second moments, there exists a D2 geodesic mu t with these endpoints, connecting them, along which the map T is, I want to say can convex, and that's almost true. But I need to multiply k by the distance between the endpoints. Right, so in other words, if you go back to the definition of can convexity, if you rescale the argument R, it's like multiplying the k by the rescaling parameter squared. And if I had parameterized this geodesic by its arc length, then indeed I would write can convexity here. But unless the geodesic has unit length, I can't parameterize it by its, if I parameterize it by its arc length, it's not going to be parameterized over the unit interval, it's going to be parameterized over some other interval. And so I need to adapt the notion of k to the length of the interval, the actual length of the geodesic that I'm parameterizing on the unit interval. Is it clear? Okay. So the first examples of spaces that are Kn convex. Oh yes, and one more little subtlety. So this definition that I've chosen is what's sometimes called entropic. So there's sometimes you write a little e here. So this is not the original definition. So it's entropic curvature dimension condition. The original definition involved a more complicated entropy than this one that depended, an entropy that depended on n. Under reasonable conditions, these definitions turn out to be equivalent, and I just find this one simpler to work with. So the original definition came out of these papers of Lott, Fulani, and Sturm between 2006 and 2009. This definition that involves only the rho log rho entropy, independent of what parameter n we're dealing with, comes from a later paper by Urbar, Kuvada, and Sturm in Invenciones, I think about 2015. So the original definition came out of Lott and Fulani in 2009 and Sturm in 2006. Okay, anyhow, so the curvature dimension conditions came out of Sturm's work, and the entropic curvature dimension conditions comes out of Urbar, Kuvada, and Sturm's work, and then there's several papers involved in showing their equivalent. Great. So what are some example spaces that satisfy it? So the simplest examples are just given by intervals. So take Euclidean distance on an interval. For example, the interval x is less than pi over 2 times square root n minus 1 over k. But you can still impart some curvature to, although the Euclidean distance is not curved in any way. So the sectional curvature is 0, if you like. You can still get some Ricci curvature by choosing a measure which is different from the Lebesgue measure. So let our measure be, instead of Lebesgue measure, let it have a density like cosine of x times the appropriate multiple of and if n is different from 1, you'd put an exponent n minus 1 here. So that's for k bigger than 0. And you can imagine for k less than 0, you choose hyperbolic cosine instead of cosine. So in case k equals 0, you choose the positive half interval, and you choose a measure that's given by a power n minus 1 of x. And that should be reminiscent a little bit of when you do a change of variables to polar coordinates in dimension d, you get a factor like r to the d minus 1 dr. So that's the same capital N minus 1 here. You can do the whole line, provided you put this hyperbolic cosine. And so far, this is all finite n. And if we wanted infinite n, we could, again, take x in r, but this time we'd have an exponential factor. And sorry, I'm sort of using a notation that I don't usually use, but and so you could put a Gaussian factor, and the Gaussian would the variance of the Gaussian would depend on how much curvature you want, or it would be an exponentially growing factor if k is negative. And so I'm not going to verify today that these examples satisfy the condition, but maybe we'll do that. Maybe we'll do something slightly more general in a future class that implies that these examples satisfy the condition. And so I think that I'm using Sturm's notation here. So I would tend to write this in the form dm of x, but Sturm and some probabilists tend to write m dx. But anyhow, what it means is it's absolute continuous with respect to Lebesgue, and the density with respect to Lebesgue is given by this factor. Questions?
So is the factor of the square root of k over n minus 1, is that inside the cosines or inside the argument of the cosines?
Yeah, it's
okay.
inside the argument. Yep.
Thank you.
Other questions? And I'm probably going to drop the entropic. And oh yes, sometimes in well, you don't see this in the literature much, but so we used Wasserstein 2 distance to define the distance on probability measures, and therefore the geodesics on probability measures. You can also, if you do this with, if we had done dp here, you would get a possibly slightly different notion, which depends on p. Although I believe again that so the p naught equals 2 was introduced by Kell. And so I have a paper with co-authors, including Affini Academia, who may or may not be attending today, showing that, in fact, this definition is independent of P. The set of spaces which satisfy it don't depend on P in the end. So the P is always bigger than 1 in this story. Okay, we show that they don't depend on P under some non-branching hypothesis. So we need to make some assumption that says that in the underlying space, you never have two geodesics which go along together for a while and then split off in different directions. Okay, but all that's sort of a subtlety that came later. So I guess you shouldn't be too surprised to see these cosines and hyperbolic cosines coming up, given that those are the prototypical examples of Kn convex functions are these guys here. So of course the exponential, whatever, complicates things a little bit, but but it's a bit like the exponential that appears in the Gaussian. Okay, so let me see if I can try to get, I was hoping to do the Brunkowski inequality to show, which is kind of the first non-trivial consequence. Gosh, I'm probably, maybe it's too little time. Maybe I'll state the theorem and then we can see how far we get. So, so here's the proposition. This is the generalized Brunkowski inequality. And the claim is that if MDM, if our metric measure space satisfies this entropic curvature dimension condition with n finite, then whenever you take a pair of Borel subsets in the support of the measure, and t between 0 and 1, you get that the, let's say the outer measure, oh yes, so I need a definition here. So let me define the set of midpoints at time t between x and y to be the set of z in M such that there exists x in capital X and y in capital Y with little z lying on the geodesic joining little x to little y and separating them by time t. So such that dxz is proportional to dzy is proportional to dxy with proportionality constants given by t and 1 minus t. So in other words, as t goes to 0, that forces z to be close to x, and as t goes to 1, it forces z to be close to y. And the fact that these things add up to the distance between x and y combining with the triangle inequality implies that that little z is on the geodesic, is on a geodesic joining x to y. So the picture is you take x here and y over here, and then, for example, when t is 1/2, you'd look at the set of midpoints. So every point in z 1/2 of xy would lie on it at the midpoint between a geodesic starting in x and ending in y. And so then the generalized Brunkowski inequality says exactly what the usual Minkowski inequality said in Euclidean space. It says that the measure of this set of midpoints is at least as big as the combination of the measures of the set, as the convex combination of the measures of the set of endpoints in case k is 0, and a weighted convex combination of the measure of the set of endpoints in case k is non-zero. So this is a definition for z, and the conclusion of the theorem is the measure of zt of xy is always bigger than, and the same factors sigma are going to come into this. Sigma k over n 1 minus t, we could put, let's see, let's put capital theta here, the measure of x to the power 1 over this putative dimension parameter capital N that appeared in the definition of the curvature dimension condition. And okay, so there's a little issue. We haven't, even if capital X and so this is capital X and capital Y here. Even if they're measurable, it's not so clear that this set of midpoints is measurable. So let's take this to be the outer measure corresponding to M. And what is the theta? So the theta is the distance between capital X and capital Y. If k is positive, and it's the maximum if k is negative. And it's irrelevant. You can take it to be 1 if k is 0, because the sigma is just 1 minus t independent of theta when k is 0. And so really what you would expect to appear here, you'd really expect something like the 2 Wasserstein distance between a uniform measure on x and a uniform measure on y to appear in place of theta as the argument of these 2 factors sigma. And what's really going on is that the sigma is monotone in theta, and the 2 Wasserstein distance always lies, let me call this theta lower and this theta upper. This 2 Wasserstein distance always lies between theta lower and theta upper. That's pretty clear. And depending on the sign of kappa or k, the sigma is either monotone increasing or monotone decreasing. And so when k is positive, you can replace this by its lower bound and get a weaker inequality. And when k is negative, you can replace this guy by its upper bound and get a weaker inequality. But the point of these weaker, I mean, it would be a stronger inequality to replace theta by the actual distance between the uniform measures on x and y. And the reason we don't, maybe the theta lower and theta upper are maybe more geometrically elementary quantities to define on the one hand. And maybe on the other hand, you can worry about if x and y don't have positive measure, that these uniform probability measures aren't defined. And so this works even for sets which maybe have 0 measure. Okay, so I think that I am not going to try to, I'm happy to have stated it. I'm not going to try to prove it today, but we'll prove it next class, that this kind of Brunkowski inequality holds not only on Euclidean space with Euclidean volume and Euclidean distance, but on any metric measure space that satisfies the entropic curvature dimension parameter condition with any parameters n and k, provided that n is not infinity. You have to modify it. There is an analogous statement when n is infinity, but it's a little bit weaker and you have to modify it. Okay, any questions? And other consequences you get from this Brunkowski inequality are things like, well, we're going to see you get a kind of what's called the Bishop-Gromov inequality, which is of the flavor of, has some isoparametric flavor to it. It tells you things about the surface area of spheres and balls and how they change the radius of the sphere. It gives you a monotonicity of the surface area of the sphere in the metric space as the radius of the sphere increases or decreases. And you also get doubling properties when n is finite, and which say if you double the size of the ball, its measure doesn't go up by more than a bounded factor. And that implies things like that the Heine-Borel property, if n is finite, that closed bounded sets are compact in these metric measure spaces when they satisfy an entropic curvature dimension condition with finite dimension parameter capital N. Okay, if there are no on the record questions, I'll stop the recording.